Hi, my name is Jeremy Smith, and today I'll be presenting to you my final presentation for Euclidean geometry this semester. And this presentation is a proof of the converse of the alternate interior angles theorem, which states that in Euclidean geometry, if two parallel lines are cut by a transversal, then both lines of alternate interior angles are congruent. Now we're going to prove this by using a proof by contradiction. First, we'll accept our three premises: one, that vary in Euclidean space, that the Euclidean postulate holds true; two, that we have two parallel lines; and three, that our two parallel lines are cut by a single transversal. Then we're going to assume the opposite of the consequence in the statement. So in this case, we'll assume that the alternate interior angles are not congruent. And finally, we will arrive at a contradiction of one of our premises, and in so doing, that demonstrates that our assumption is false, and we conclude the opposite is true. Before we begin, we will start by reviewing a few basic definitions. First, the definition of a parallel lines are two lines that share no common point, that is, they never intersect. The Euclidean parallel postulate states that given a line L and a point P not on L, there exists only one line that passes through P which is parallel to L. The definition of alternate interior angles is that when you have two lines and a transversal which cuts through both lines, the angles which are located on the interior of the two lines and on opposite sides of the transversal are called alternate interior angles. And the alternate interior angles theorem states that if L and L prime are two lines cut by a transversal T in such a way that a pair of alternate interior angles is congruent, then L is parallel to L prime. So now we begin our proof, first by accepting the premises. And our three premises are that M and N are parallel lines, that they are cut by a transversal T, and that we are in Euclidean geometry. When we do that, we see that M and N intersect with T at points A and B respectively. Also, we see that this creates two pairs of alternate interior angles. Pairs angles 1 and 4 and angles 2 and 3. Next, we state the goal for this proof. We aim to show that both pairs of alternate interior angles are congruent. That is, that 1 is congruent to 4, and that 2 is congruent to 3. Next, we're going to build our argument by contradiction. And to do so, we're going to first only consider one pair of alternate interior angles. So we're only going to consider angles 1 and angles 4. And now we're going to assume that angles 1 and angle 4 are not congruent. This implies that one of two cases is true. Either 1 is less than 4, or 1 is greater than 4. So now we build an argument for case 1 of our assumption. In case 1, angle 1 would be less than angle 4. If angle 1 is less than angle 4, then it is reasonable that there exists some line K which intersects with T at point A such that there is an angle 5 which is alternate interior incongruent to angle 4. And so we can look at this diagram here and we can see that K is a line which intersects T at point A, and we're saying that angle 5 here is congruent to angle 4. But if angle 5 is congruent to angle 4, then by the alternate interior angles theorem, lines K and N are parallel. But if K is parallel to N, and by assumption N is parallel to M, and both K and M go through point A, this is a contradiction of the Euclidean parallel postulate. So therefore we can conclude that 1 cannot be less than 4. So our second case is that angle 1 is greater than angle 4. So once you use a similar argument that you used with case 1, you'll obtain the result that angle 1 cannot be less than angle 4. And this diagram here depicts that in this case, again, angle 5 will be congruent to angle 4. And again, by auxiliary angles, this would be that line K is parallel to line N, but line N is already parallel to line M, and K and M both pass through point A. So because we just proved that 1 is not less than 4, and also that angle 1 is not greater than 4, then we must conclude that angle 1 is congruent to angle 4. So now let's recall our goal. Our goal was to show that both pairs of alternate interior angles are congruent. As of now, we've shown that angle 1 is congruent to angle 4. However, we can use a similar argument that we used for angles 1 and 4 to show that angles 2 and 3 are also congruent. So when we do this, we can conclude the following statement. In Euclidean geometry, if two parallel lines are cut by a transversal, then both pairs of alternate interior angles are congruent. And this statement is, in fact, the converse of the alternate interior angles theorem, which is what we were trying to prove. Thank you.